What about other objects still? Okay. Let's think again about what we got in lower dimensions. A line in R3 can be described as the intersection of two planes, right? I can write a line in R3 by writing both equations, general equations of the two planes, and then saying, okay, my line is the intersection of those two planes. Now, notice one thing. In this system, we have three variables, okay? And we have only two equations, right? So that means that we're going to end up with one free variable. That free variable is the one that is going to be scanning the line and therefore defining the line. Okay, so we're going to use this idea to figure out another way to describe k-dimensional objects. Okay, so a straight object of dimension k in Rn can also be described as the intersection of n minus k hyperplanes. Okay, okay, let's make sense of all these letters and where they come from. Okay, so if I take n minus k hyperplanes, okay, so look at this system. It's made up of n minus k equations, and it has n variables, right? So how many free variables can it have? Well, it may have more than that, but at least it will have n minus k, and if you do the algebra, it turns out to be just k free variables. Those k free variables are going to identify the k directions in which this k-dimensional object will go, and therefore that's the one way to identify these k-dimensional objects. So either with the vector equation that we saw earlier, or with the parametric equation, or with as the intersection of hyperplanes as it is done in this approach. For instance, let's have a look at what we're seeing here. So for instance, if I'm looking at a line in R4 now, okay, so a line in R3, we know it's the intersection of two planes. Well, how about a line in R4? Well, it's going to have to be the intersection of three hyperplanes, right? So in this case, we have three equations, four variables. That means at least one variable is going to be the free variable, assuming that we have chosen the hyperplanes correctly. That is all the free variables we're going to have, and therefore that's going to define our line. On the other hand, if I look for a plane in R4, well, let's think about it. A plane will have dimension 2 in R4. The difference is 2, so that means I'm going to need two equations of two hyperplanes. So a plane in R4 is going to, remember, a plane is a two-dimensional object, eh? It's going to be given by the intersection of two hyperplanes. So, can you visualize a line in R4 or a plane in R4? Is it starting to look a little bit difficult? Well, probably you won't be able to visualize them. In fact, I looked on the internet to see if I could use any nice pictures, videos, or something like that for these higher dimensional things. I didn't really come up with much except for several videos that try to describe what a hypercube looks like. So that tells you how difficult these visualizations are. So we're going to try and work with these things algebraically, try to visualize as much as we can, go back to the analogy to geometric vectors, and just try to build up our understanding of them as we go along.